Number 68. An organic compound has a composition of 93.46% carbon and 6.54% hydrogen by mass. A solution of 0.090 grams of this compound in 1.10 grams of camphor melts at 158.4 degrees Celsius. The melting point for pure camphor is 178.4 degrees Celsius, and the Kf for camphor is 37.7 degrees Celsius per molality. Assuming ideal solution behavior, what is the molecular formula of the solute? Show your calculations. Okay, strap in those shoelaces, guys, because we're going on a wild ride, but we got this. So they're throwing us a lot of numbers, right? They're throwing us percentages by mass. We have how much, grams of the solution that we have, right? Of the compound. We have a 1.10 gram sample of camphor. They gave us the melting point of pure camphor and a Kf value, but ideally we want to find out what the molecular formula is and the molecular formula of the specific solute. Now, keep in mind that the solute is always the smaller amount that is placed inside of the solvent. And together, a solute and a solvent is always going to make up the total solution. Now, they do say that we have this total solution that corresponds with the 0.090 grams of this compound in the camphor. The solute always gets dunked into the solvent. So by this wording, we know that the 0.090 grams of the compound, which is placed in the camphor, that secret compound, we'll say compound, that's the solute. And the solvent has to be the camphor. And together, they make up the total solution, right? So let's just, maybe I'll write it somewhere. Maybe we'll write it down here because this is not really that important. So the solute is some type of compound which we don't know the formula for, right? That's why it's asking for find the molecular formula. And the solvent is the camphor. And together, the secret compound plus the camphor makes up the sol solution. But anyway, now they're asking for a molecular mass, and the first thing that they give me is percentages by mass. Now, if we just pretend that this, couple of next sentences don't exist, and they give us a percent by mass, and they want us to find the molecular formula, I know a roadmap that can lead me from percentages to molecular formulas. It's pretty long, but I know it, and that's this right here. The long roadmap of going from a percent all the way to a molecular formula. So chances are we're going to be running through this. Now, the reason why I knew that we were doing this is because anytime that they give you percents of individual elements, you can always find an empirical formula from that. The only thing is that now we just have to take the empirical formula, which we'll find out, and get to a molecular formula. So, let's start. They did tell us that we had 93.46% of carbon, and they did tell us that we had 6.54% of hydrogen. So we're all the way over here. So the first thing is just make sure that you don't have any hidden percentages, right? The total percent of any sample is always 100. But I look here, 93.46 plus 6.54, that equals to 100. So you could always just double check that. But now I want to take that percentage and just go to grams. How do I go from percent to grams? Well, we can assume that since the whole sample is 100%, we can say that that was the total amount of grams that we had. We don't know how many grams we actually had, but we can make a standard and say that, okay, so since everything is out of 100%, I can say that everything was out of 100 grams. And because of that, we can say that the percentage equals the grams. So out of the 100 gram sample, I have 93.46, and maybe I'll do it here, grams of carbon. And I have 6.54 grams of the hydrogen. So now I'm at this stage. Now I want to go from grams to moles because I'm getting closer. I'm getting closer to what I want, that molecular formula. Grams to moles. Well, that's going all the way back to the beginning of chemistry. Grams to moles, we could always just divide by the molar mass. So I have to go on the periodic table to find out what the molar mass is of carbon and hydrogen. So I guess what I'll do is we'll just say this divided by the molar mass, right? Or maybe I could just, put it over the number, but I guess we'll just do this, right? So on the periodic table, right, I just got to look up what the grams are. And for carbon, looks like it's 12.01, right? 12.01 grams per mole. So I'm just going to take that 93.46 and divide by the 12.1. So 93.46 divided by 12.01. Okay, and I get roughly 7.7818. And that's now the moles of the carbon. Make sure to do every step for both elements as you go. Don't do all of carbon, try to get over here and then go back. So let's find out the moles of the hydrogen. So I'm going to divide by the molar mass on the periodic table for hydrogen. And on mine, it's 1.008. So 6.54 divided by, what happened? Sometimes I press the wrong button. 6.54 divided by 1.008. Probably going to be roughly the same. 6.48810. That's good enough for me. Okay, so now we're at the mole stage. Next, we have to find a mole ratio. Now, a ratio, keep in mind, is always just a number divided by some other number. So we know that, once again, we are going to be doing division. So maybe what I'll do is I'll just maybe lower this a little bit. I'm going to take my 7.7818 divided by a number and 6.48810 divided by a number. But the question is, what is the number on the bottom? Well, we can kind of go to the next step to figure out what it is. We always want to get to an empirical formula. Empirical formula first and then molecular formula. But the empirical formula is always the lowest subscripts. It's the lowest ratio. So what you're going to do to find your mole ratio is you're going to divide by the smallest number. So I have to look between 7.7818 and 6.48810 and divide by the lower number. 6.48810 is the lower number, so we're going to divide by that for both numbers. 6.48810. So I'm going to say divide by lowest. So this obviously comes out to being 1 mole of hydrogen. And now let's see how many moles of carbon I have. So I'm going to take this number and divide it by the hydrogen number. And I get, oh boy. Technically at this stage, you should get whole numbers. But now here, this would round to like 1.2 moles of carbon. This too, it's not low enough to just say that it's 1 mole of carbon. 1 mole of carbon would maybe look like 1.009 something on the calculator. Then you can definitely round. But 1.2, I don't like that. But at least we have the mole ratio. Now the thing here is that we don't like mole ratios to be in decimal form. So what we have to do is we have to kind of do some trial and error. where I want to make this number into not a decimal. I want it to be a whole number. So you're just going to, process of elimination, always start with the lower number and just keep going up until you get a whole number. But what you're going to do is you're going to take the 1.2 and times it by some number. And the idea here is that you want a whole number at the end. So 1.2 times 1 would just be 1.2. So I'm not going to start there, but maybe times by 2, right? So let's see, 1.2 times 2. Will that get me a whole number? Nope. So I just keep going up. 1.2 times 3. No, 3.6. 1.2 times 4. 4.8. 1.2 times 5. There you go. So by timesing by 5, I get a 6. And that's my new moles of carbon. 6 moles of carbon. However, you have to be fair. Whatever number you multiplied by the carbon, you have to multiply by the hydrogen. You got to be fair. So 1 times 5 is now 5 moles of hydrogen. And the last but not least thing here is we can find our empirical formula because we now have the lowest whole numbers. So maybe I'll put it up here, right? My empirical formula is going to be C6H5. Okay. So we are finally here. So it seems like we're like one step more, right? Now, keep in mind that if we want to find the molecular formula, the next step is to always take your molecular mass, which is called a molar mass, right? A molecular mass, a molar mass. I just said molecular because it's coming from the molecular formula. But this is the same thing as molar. But specifically, it's coming from your molecular formula. You take that number and you divide it by your empirical mass. Because what you want to find out is how much more is that molar mass than the empirical mass that you have. Now with C6H5, I can find my empirical mass, right? If I have an empirical formula of C6H5, C6H5, the formula, right, on the periodic table, we have 6 carbons, so 6 times 12.01 plus 5 times the mass for the hydrogen, 1.008, 6 times 12.01 plus 5 times 1.008, and I get roughly a empirical mass of 77.1. And that's the number that goes on the bottom. However, do I have a molecular mass? They didn't say, right? They just said that we had 0.090 grams of this compound. But they didn't say specifically what the molar mass or the molecular mass is. Remember that a molar mass, or a molecular mass, I guess we'll say molar mass, is always the grams that you have of that compound divided by the moles. So in order to find out this molar mass, I should have the amount of grams of that compound divided by the number of moles of that compound. So let's see, do I have both of those? The molar mass would be equal to, well, actually they did tell me. They told me that we had 0.090 grams of the compound. Keep in mind that I don't care about camphor because camphor was not the solute. Camphor is the solvent, and we want that molecular formula for the solvent. We want the molecular formula for the solute. So we do know that we have a 0.090 gram sample, but did they tell us how many moles we had? Not that I know of. So now this is the missing link. So we're starting to put the pieces together, where if I can find out how many moles of this compound I had, I can find the molar mass. And if I have the molar mass, I could find out the timesing factor when I divide it by the empirical mass. And once I find that number out, I can find the molecular formula. So the missing link here now is get those moles. So now where do we go from here? Well, maybe let's make like a little box here, just so that we don't lose sight of, where we're at. But now they're bringing in all this solution information. We still have to use the 1.10 grams of the solvent, the camphor, and they gave us a melting point, right? They told us that the pure melting point of camphor was 178.4, and they gave me a KF value, the one that has units. That's the freezing point depression constant. So, I know a formula that uses a KF value, and that's this right here. So let's see, maybe we can work with this now. Now, delta TF is the change in the freezing point. Okay, well, let's see. All they're talking about is melting. But wait a minute, right? If this formula is set for freezing, but they're giving me melting, how is that going to work? Well, keep in mind that melting is from a liquid. Actually, melting is from a solid to a liquid, right? Solid to a liquid is melting. And that happens at a certain temperature. In this case, for pure camphor, it would be 178.4 degrees Celsius. But if this formula is set for freezing, freezing by definition is the liquid turning back into the solid. These are just opposites of each other. However, these processes occur at the same temperature because you're just going back and forth between a solid to liquid to solid. So I can treat all of these as if it was freezing. And now I can start using my formula. Now, the pure melting point or the freezing point, right, because they're opposites now, is 178.4. But now we know that this solution melted at 158.4. We want to find that change. And whenever you want to find a change, that's always going to be subtraction. Delta TF is always going to be a positive value. So we just take these two temperature values and subtract them in a way so that you get a positive value for your delta T. So in this case, we're going to take the pure camphor because that's higher, right? The pure one was 178.4 degrees Celsius minus the solution one. And the solution temperature was 158.4 degrees Celsius. So if I just subtract these two, 178.4 minus 158.4, I get 20 degrees Celsius. And that is my delta TF. They already gave me a KF value. The KF for camphor is 37.7 degrees Celsius per molality. Now the next thing is, well, I know that I'm not going to know one unit, right? Is it the cute little m here, which is molality, or is it the I value? Well, in order to solve for molality, I do need the moles of that solute divided by the kilograms of solvent. But, we run into the same problem here. I don't know the moles of the solute. And if you don't know the moles of the solute, I can't find out my molality. So chances are this is what I'm solving for. So I should know my I value. And the I value is called the Van 't Hoff factor. The Van 't Hoff factor just basically determines if a solute is either an electrolyte or a non-electrolyte. If it is a non-electrolyte, your I value is going to be 1. But if your compound starts dissolving into different ions, that's an electrolyte, and your I value is going to be anywhere from 2 to, 3, 4, 5. But this all comes down to what elements are in your solute. Now in this case, we have two elements that are in the solute, carbon and hydrogen. Would this be an electrolyte or not? Well, carbon and hydrogen, these are all nonmetals. And the only type of element, or the only type of compound that nonmetals can make are covalent. And if you have a covalent compound, you will be a non-electrolyte. So we know that this covalent compound is a non-electrolyte. Whoop. Oh boy, I could fit an E in there. And because of that, my I value equals 1. Now I have my delta TF, my KF, my I value. I can solve for the molality. Let's go for it. So I got 20 equals 37.7 times X. And then if you want to, we can times by the 1. But anything times by 1 is itself. So, you don't have to worry about it. But basically, you want to get X by itself. So you will divide on both sides by 37.7. And let's see the molality. So we have 20 divided by 37.7. And I get a molality of 0.531 molality. Okay, so we're running out of room here. But what I'm going to do is maybe we will transfer this information up here. Oh boy. Do we really need this? I guess maybe a little bit. Maybe we could keep it down here. But the next step here is to now use this molality to use a different formula. And just like we said, the molality equals the moles of the solute divided by the liters of solution. So maybe if I just kind of move this over here, and we're getting down to it. We're getting down. We just found out the molality, which is 0.531 molality. And which one don't we know? Do we not know the moles of the solute? Or do we not know the kilograms of the solvent? Well, they did say that we had 1.10 grams of the camphor. That's the solvent, right? We said that the solvent was the camphor. So in this case, I know that I have 1.10 grams, but we need kilograms. How do we go from grams to kilograms? Oh, that's dividing by 1,000. Similarly, you could take the decimal, move it to the left 3 times. So 1.1 divided by 1,000. You get 0.00, maybe I'll write it in blue, 0.0011 kilograms. And now we're just going to solve for the solute. And whoop, let's see, can I bring this up a little bit? I might start getting rid of some things just because we have not really too much room left. But let's see. So we have 0.531 equals 0.0011, and then we're just solving for the moles. So it seems like just a quick cross multiplication. So I'm going to take the kilograms and times them by the molality. And I get X equals 5.8, I'll just put 5.84 moles. Oh, 5.84 times 10 to the negative 4th moles. Okay. So now, this is the link to where we were trying to get to before, right? We finally found those moles. And if we want to find that molecular formula, I got to find that molar mass first. Molar mass equals grams divided by moles. We did already place in that we had 0.090 grams of the compound. And now we know that the number of moles that go along with it is 5.84 times 10 to the negative 4th. So let me just move this down And maybe what I can do, I have a little room here. Making moves. Let's find out that molar mass. Molar mass equals 0.09 divided by this number. I get 154. Okay, so 154.2 grams per mole. And grams per mole. Okay, really sorry that it's all over the place, but I think we can do it. Okay, so now we have the empirical mass. Remember we calculated that from before, 77.1. Now we just take the molar mass and divide these two. So the molar mass was 154.2, and I'm going to divide that now by the 77.1 that we did before. So we have this number divided by, and was it just 77 point? It was just 77.1. Divide those two, and whoa, you get very, very close to a whole number. This is 2. That means that my molecular formula should be 2 times more than the empirical formula. We stated that the empirical formula was C6H5. But now since we know that we are 2 times more, I'm going to take the subscripts and times them by 2. That's all you got to do. So 6 times 2, 5 times 2. We finally get a molecular formula of C12H10. And that is the final answer. Wow. I told you it'd be a rough one, but if you could do this one, I promise you could do whatever you need to do in this course. This one was a crazy one. And thank you for sticking around for the ride, right? It's for these, I mean, once you get the answer, it's really rewarding. You worked so hard. We've been at this question for like 5.5 hours. And then once you get the numbers in place, you're coming out with a beautiful whole number over here, 2.000. You know you did it. You know you did it well. So I'm really glad that this helps you out. Thank you, and I'll talk to you in later lessons, okay? All right. And if you wouldn't mind, please hit the subscribe button. It just gets the word out there that this YouTube channel exists. And it's all because of you guys that this channel's growing. So thank you, thank you, thank you. And I'll talk to you soon, okay? Have a great day. Bye-bye.